NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math tutorial. Today, we'll verify whether the given radical equalities are correct. Let's start with our first example. We want to verify if the square root of 2 times the square root of 32 equals 8. Let's verify this step by step. First, we'll write out the left side of the equation, the square root of 2 times the square root of 32. Now, we'll apply the rule for multiplying square roots. When we multiply square roots, we can combine them under a single square root. So the square root of 2 times the square root of 32 equals the square root of 2 times 32. Next, let's calculate what 2 times 32 equals. 2 times 32 is 64. Finally, we need to find the square root of 64. The square root of 64 equals 8. So we have verified that the square root of 2 times the square root of 32 is indeed equal to 8. The given equation is correct. Now, let's move on to our second example. We want to verify if the cube root of -9 times the cube root of 3 equals -3. Let's start by writing out the left side of the equation, the cube root of -9 times the cube root of 3. Now, we'll apply the rule for multiplying cube roots. When we multiply cube roots, we can combine them under a single cube root. So the cube root of -9 times the cube root of 3 equals the cube root of -9 times 3. Next, let's calculate -9 times 3. -9 times 3 equals -27. Finally, we need to find the cube root of -27. The cube root of -27 equals -3, because -3 cubed is -27. So we have verified that the cube root of -9 times the cube root of 3 is indeed equal to -3. The given equation is correct. Let's summarize what we've learned. We've verified 2 radical equalities. First, we confirmed that the square root of 2 times the square root of 32 equals 8 by using the product rule of square roots. Second, we verified that the cube root of -9 times the cube root of 3 equals -3 using the product rule of cube roots. Remember, when working with radical expressions, you can multiply radicals of the same index by multiplying what's inside and keeping the same radical. Simplify calculations step by step to verify equalities. Be careful with negative numbers, especially with even root indices. Try practicing more examples to improve your understanding of radical expressions. Let's see how we can use the properties of cube roots to show that these equalities hold. Let's start with our first example. We need to show that the cube root of b, a squared times the cube root of ab squared equals ab. To solve this problem, we'll use the rule for the product of cube roots. This rule states that the cube root of x times the cube root of y equals the cube root of x times y. Let's apply this rule to our problem. Step 1. Combine the cube roots into 1. Using our rule, we can write the cube root of b, a squared times the cube root of ab squared equals the cube root of their product, which is ba squared times ab squared. This simplifies to the cube root of a cubed times b cubed, which we can rewrite as the cube root of ab cubed. Step 2. Use the fact that the cube root of a cube is the base. We know that the cube root of anything cubed equals that thing itself. So, the cube root of ab cubed equals ab. Therefore, we've proven that the cube root of b, a squared times the cube root of ab squared equals ab. Now, let's move on to our second example. We need to prove that the square of the cube root of a equals the cube root of a squared. For this problem, we'll use the rule for the power of a cube root. This rule states that when we raise a cube root to a power, we can also bring the power inside the cube root. Step 1. Interpret the square of a cube root as a product. We can write the square of the cube root of as the cube root of a times itself. Then, using the product rule for cube roots that we saw earlier, this equals the cube root of a times, which is the cube root of a squared. Therefore, we've proven that the square of the cube root of a equals the cube root of a squared. We need to multiply the square root of 0.2 times the square root of 0.18. Our first step is to convert these decimals into fractions, which makes it easier to work with square roots. 0.2 equals 2 over 10, and 0.18 equals 18 over 100. Now, we'll apply the product rule of radicals which states that the product of square roots equals the square root of the product. This gives us the square root of 2 over 10 times 18 over 100. Step 3. Multiply the fractions inside the square root. To multiply fractions, we multiply the numerators together and the denominators together. So we get 2 times 18 over 10 times 100. In step 4, we'll simplify the fraction inside the square root. 2 times 18 is 36, and 10 times 100 is 1,000. So we have the square root of 36 over 1,000. For step 5, we'll rewrite this as a product to make it easier to simplify. We can rewrite this as the square root of 1 over 10 times the square root of 36 over 100. In step 6, we'll use the product rule of radicals in reverse. This gives us the square root of 1 over 10 multiplied by the square root of 36 over 100. Step 7, we'll simplify the square roots. The square root of 36 equals 6, so we have the square root of 1 over 10 multiplied by 6 over 10. Finally, let's express our result in a more standard form. 6 over 10 simplifies to 3 over 5. Now, let's take a more complex example. We need to find the product of negative 5 times the square root of 6 and negative 2 times the square root of 18. Our first step is to group the coefficients and the radicals separately. We multiply negative 5 times negative 2, which equals positive 10. Then, we have the square root of 6 times the square root of 18. Step 2, we multiply the coefficients. Negative 5 times negative 2 equals positive 10. In step 3, we'll apply the product rule of radicals. The product of square roots equals the square root of the product, so we get 10 times the square root of 6 times 18. Next, we'll multiply the numbers inside the square root. 6 times 18 equals 108. Step 5, we'll factor out any perfect squares from under the radical. 108 can be written as 36 times 3, and 36 is a perfect square. In step 6, we'll use the product rule in reverse. This gives us 10 times the square root of 36 times the square root of 3. Next, we'll simplify the square root of 36. The square root of 36 equals 6. In our final step, we multiply the coefficients. 10 times 6 equals 60, so our answer is 60 times the square root of 3. Let's summarize what we've learned about multiplying radical expressions. First, we can use the product rule to combine radicals. The square root of a times the square root of b equals the square root of a times b. Second, when working with decimal numbers, convert them to fractions to make calculations easier. Third, always look for perfect squares under the radical and simplify them. And finally, when multiplying expressions with coefficients, multiply the coefficients separately from the radicals. With these techniques, you can multiply any radical expressions efficiently. We want to calculate negative 3 times the square root of 5 times negative 2 times the square root of 20. To solve this problem, let's first separate the numerical coefficients from the radical parts. We have negative 3 times negative 2 multiplied by the square root of 5 times the square root of 20. Next, we multiply the numerical coefficients. Negative 3 times negative 2 equals positive 6. So we have 6 times the square root of 5 times the square root of 20. Now, we apply the rule for multiplying square roots. The square root of 5 times the square root of 20 equals the square root of 5 times 20. Let's calculate 5 times 20, which is 100. The square root of 100 is 10, so we have 6 times 10. Finally, we multiply 6 times 10 to get 60. So our answer is 60. Now, let's move on to our second example. Here we need to calculate the cube root of negative 2 times the fifth root of 5. Let's first rewrite this as the cube root of negative 2 times 5. Now, we compute negative 2 times 5, which is negative 10. So our final answer is the cube root of negative 10. Note that this cannot be simplified further because negative 10 is not a perfect cube. For our third example, we'll verify that the square root of 14 times the square root of 7 times the square root of 2 equals 14. First, let's apply the rule for multiplying square roots. We combine the expressions under the radical sign by multiplying them. Now, let's multiply the values under the radical. 14 times 7 is 98, and 98 times 2 is 196. The square root of 196 is 14, because 14 squared equals 196. So we verified that the square root of 14 times the square root of 7 times the square root of 2 does indeed equal 14. Let's recap what we've learned about working with radical expressions. We need to calculate the cube root of 9 minus square root of 17 times the cube root of 9 plus square root of 17. In the first step, we'll rewrite this expression using a property of cube roots. When we have the cube root of a times the cube root of b, we can rewrite it as the cube root of a times b. So we get the cube root of open parenthesis 9 minus square root of 17 close parenthesis times open parenthesis 9 plus square root of 17 close parenthesis. For the second step, we'll apply the difference of squares formula. We know that a squared minus b squared equals a minus b times a plus b. In our case, we have 9 minus square root of 17 times 9 plus square root of 17, which is equal to 9 squared minus the square of square root of 17. In the third step, we'll simplify what's inside the cube root. 9 squared is 81, and the square of the square root of 17 is simply 17. So we have the cube root of 81 minus 17. For our fourth step, we'll perform the subtraction inside the cube root. 81 minus 17 equals 64. In the fifth step, we'll rewrite 64 as 4 cubed. Since 64 is equal to 4 to the third power, we have the cube root of 4 cubed. For the sixth step, we'll apply the property that the nth root of a to the nth power is simply a. Since we have the cube root of 4 cubed, this simplifies to just 4. Let's move on to our second example. We need to calculate the fifth root of 3 times the fifth root of 9 times the fifth root of 3/5 times the fifth root of 5/9 times the fifth root of 27. In the first step, we'll apply the property that the product of nth roots is equal to the nth root of the product. So we get the fifth root of 3 times 9 times 3/5 times 5/9 times 27. For the second step, we'll perform the multiplication inside the fifth root. First, let's multiply all the terms inside the fifth root. We have 3 times 9, which is 27. We also have 3/5 times 5/9, which equals 15/45, which simplifies to 1/3. And finally, we multiply by 27. So we get the fifth root of 9 times 27. In the third step, we'll continue simplifying inside the fifth root. 9 times 27 equals 243. For the fourth step, we need to express 243 in a more useful form. We can write 243 as 3 squared times 3 cubed, which is 3 to the fifth power. In the fifth step, we'll apply the property that the nth root of a to the nth power is simply a. Since we have the fifth root of 3 to the fifth power, this simplifies to just 3. We need to calculate the product of two radical expressions, 2 times the square root of a to the fourth power times b, multiplied by 3 times the square root of a squared b cubed. When multiplying radical expressions, we need to remember an important rule. The product of radicals with the same index equals the radical of the product. In other words, the square root of a times the square root of b equals the square root of a times b. Let's begin solving. First, we rewrite this as 2 times 3, which is 6, multiplied by the product of the radicals. Using our rule, we can write this as 6 times the square root of a to the fourth power times b times a squared times b cubed. Let's use the rules of exponents to simplify the expression inside the square root. When multiplying expressions with the same base, we add the exponents. So a to the fourth power times a squared equals a to the sixth power. Similarly, b times b cubed equals b to the fourth power. Now, let's simplify the expression inside the radical. We add the exponents of like terms. A to the fourth power times a squared equals a to the sixth power. And b times b cubed equals b to the fourth power. Now, we need to simplify the radical. To simplify a square root, we look for perfect square factors. If an exponent is even, we can take out half of the power from the radical. For example, the square root of a squared equals a. In our expression, we have a to the sixth power. Since 6 is an even number, we can rewrite this as a to the third power squared. Similarly, we can rewrite b to the fourth power as b squared squared. Now we can take out the square roots. The square root of a to the third power squared is a to the third power. The square root of b squared squared is b squared. So our answer becomes 6a cubed b squared. Let's move on to our second example. Now we need to multiply the cube root of a times b times c by the cube root of a squared b to the 5th power c to the 8th power. We'll apply the same rule for multiplying radicals, but this time with cube roots. The product of cube roots equals the cube root of the product. Using the product rule for cube roots, we can rewrite this as the cube root of the product. So we get the cube root of a times b times c multiplied by a squared b to the 5th power c to the 8th power. Next, we apply the rules of exponents to simplify the expression inside the cube root. A times a squared becomes a cubed. B times b to the 5th power becomes b to the 6th power. C times c to the 8th power becomes c to the 9th power. Now we need to simplify the cube root. To simplify a cube root, we look for perfect cube factors. If an exponent is divisible by 3, we can take out 1/3 of the power from the radical. For example, cube root. To simplify a cube root, we look for perfect cube factors. If an exponent is divisible by 3, we can take out 1/3 of the power from the radical. For example, the cube root of a cubed equals a. In our expression, a is raised to the 3rd power, which is a perfect cube. B is raised to the 6th power, which is equal to b cubed squared, or 2 perfect cubes. C is raised to the 9th power, which is equal to c cubed cubed, or 3 perfect cubes. Now we can take out the cube roots. The cube root of a cubed is a. The cube root of b cubed squared is b squared. And the cube root of c cubed cubed is c cubed. So our final answer is a times b squared times c cubed. Let's summarize what we've learned today. When multiplying radical expressions with the same index, we multiply the coefficients and combine the radicals. Then we simplify the expression inside the radical by adding the exponents of like by the coefficients and combine the radicals. Then we simplify the expression inside the radical by adding the exponents of like terms. Finally, we look for perfect powers, matching the radical's index, and simplify. For square roots, we look for perfect squares. For cube roots, we look for perfect cubes. And that's how we multiply radical expressions. Before we end, here's a challenge for you to practice. Try to multiply these two radical expressions, the 4th root of x cubed y squared times the 4th root of x y cubed. Pause the video and try to solve it on your own. Then resume to check your answer. We need to evaluate the expression 2 times the cube root of a to the 4th power times b to the 3rd power, multiplied by the cube root of a squared b. To solve this, we'll use properties of radicals to simplify the expression step by step. Now, we'll multiply the expressions inside the radical. We get a to the 6th power times b to the 4th power under the cube root. Next, we can write this as the cube root of a to the 6th power times b to the 4th power. We can further simplify by using the power property of radicals. Let's rewrite a to the 6th power as a to the power of 3 times 2, and b to the 4th power as b to the power of 3 times 1 plus 1. Now, we can use the power property of radicals to separate these terms. Using the power property of radicals, we can extract powers that are multiples of the cube root. We get 2 times a squared times b times the cube root of b. Finally, we can simplify this to get our answer, 2a squared b times the cube root of b. Let's look at the problem. We need to simplify the product of the cube root of a squared plus b squared times the cube root of a to the 4th plus 2a squared b squared plus b to the 4th. Let's start by examining our expression more carefully. First, I notice something about the second radical. The expression a to the 4th plus 2a squared b squared plus b to the 4th can be rewritten as the square of a squared plus b squared. This is because it follows the pattern of a perfect square. A squared plus b squared, quantity squared. Now, let's rewrite our original expression with this insight. We get the cube root of a squared plus b squared times the cube root of a squared plus b squared, quantity squared. Now, we can use the product rule for radicals, which states that the nth root of a times the nth root of b equals the nth root of a times b, as long as the roots are the same. In our case, we have the cube root of a squared plus b squared times the cube root of a squared plus b squared squared. Using the product rule, we can combine these into a single radical, the cube root of a squared plus b squared times a squared plus b squared squared. Let's simplify what's inside the radical. We have a squared plus b squared times a squared plus b squared squared. When we multiply a squared plus b squared by a squared plus b squared squared, we get a squared plus b squared cubed. Now, we can apply the final simplification. We know that the nth root of a to the nth power equals a. In our case, the cube root of a squared plus b squared cubed equals a squared plus b squared. And that's our final answer. Let's summarize what we've learned. In this example, we simplified a complex radical expression by recognizing patterns, specifically that a to the fourth plus 2, a squared b squared plus b to the fourth equals a squared plus b squared squared. We then applied the product rule for radicals and the property that the nth root of a to the nth power equals a to arrive at our final answer. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.